Okay, guys, so the last chapter we're going to deal with is chapter 10, having to do with acids and bases. So, the first thing we really need to do is define acids and bases. So, there's a scientist named Arrhenius, who actually was the same guy who figured out, who discovered the idea of, or coined the idea of activation energy. He also did some observations with acids and bases and noticed similarities between all acids and between all bases. So we're going to talk about what his theory says about what acids and bases do. So Arrhenius, he proposed that acids and bases, the thing they have in common is that they can all be defined by what they form when they dissolve in water. So acids, an example of an acid is HCl. Right? Well, what he said was an acid, and here's another acid, H2SO4, and there's also HNO3, and there's lots of acids. Notice they'll have H in front. Well, what he says is, his theory says that hydrogen-containing compound that when dissolved in water produces hydrogen ions. So like nitric acid, you can think of it as dissociating like an ionic compound, right? It's just that the ion in question for an acid is always H+. So nitric acid breaks apart into H+ and nitrate, right? And there's hydrochloric acid. It breaks apart into H+ and chloride. Well, a base, he said, is something that when it dissolves in water, it produces hydroxide ions. Well, great, like sodium hydroxide or potassium hydroxide. So this works out pretty well. This is something that most bases have in common. There's a little bit of a... So in pure state, Arrhenius acids are covalent compounds. And so there is a covalent bond, and this is what makes acids... They're not quite covalent bonds, and they're not quite covalent compounds, and they're not quite ionic compounds. There's something in between. So when there is a covalent bond here, it's just really, really polar, and when it dissolves in water, the bond breaks, and the chlorine gets to keep all the electrons as though it were an ionic compound dissociating. So it's sort of this weird hybrid between a covalent and ionic compound. But again, the point is that it makes H+ ions when dissolved in water. And same thing with Arrhenius bases, and they're just ionic compounds that have hydroxide in them as their cation or anion. Okay, so that being said, there's a bit of a problem with this theory. It doesn't really explain why ammonia is a base. There's a problem in that later, when we think about H+, right? When we think about just hydrogen, neutral hydrogen that doesn't have a charge, what is hydrogen made up of? It's got one proton, because it's atomic number 1, one electron, and the most common isotope of hydrogen has no neutrons at all. So it's just a proton and an electron. When I write H+, what is changing? It's lost an electron. So what is it really? It's a proton. Upon realizing this is a proton, it quickly became understood that this proton can't just hang out in water. It can't just hang out by itself. It's not its own stable compound. You can have cations, but you can't have just one lone proton. That doesn't make any sense. That's not stable at all. So two other scientists came up with a better definition for acids and bases. And this is more inclusive. So it includes all of the things that the Arrhenius definition includes, but also includes other things that are observed to have acidic or basic properties. So the better definition is not that HCl dissociates in water to produce H+ and Cl-. That's actually not a very complete, good definition. And in fact, we're omitting a very important part of the process here. And that is, we're forgetting entirely about the water, right? So we have aqueous acid and liquid water. And what happens is, the Bronsted-Lowry definition is that it's not that it dissociates to form a proton, it's that it donates a proton to something else. And when you dissolve it in water, what it donates the proton to is in fact the water itself. So the water takes on a proton and becomes H3O+, right? So it's water, right? And this lone pair can go, okay, sure, I'll take that proton, and goes like that, and then it's no longer like that. But the whole thing is going to be positively charged because there's a net imbalance of protons and electrons. So this is why way back when I told you guys you didn't have to worry about hydronium as a polyatomic ion for purposes of naming ionic compounds, but it is very important with acids and bases. And then what's left over is, of course, the chloride. So this is just a slight shift in our thinking. Instead of just dissociating to leave it floundering about, it actually donates it to the water. And it's this hydronium is what gives acids their properties that we observe. Sour taste, reaction with bases. It's the hydronium that gives acids their acidic-y properties. Okay, Bronsted-Lowry base, on the converse, and this is going to seem an awful lot like oxidation reduction, right? Oxidation reduction involves a transfer of electrons. Well, the Bronsted-Lowry acid-base definition involves the transfer of protons. So a Bronsted-Lowry base is a substance that can accept a proton from another substance. This explains, so first off, you cannot have a Bronsted-Lowry acid without a base. Just like you can't have oxidation without reduction, the proton has to go from somewhere to somewhere. So it's a transfer of an H+ from the acid to the base. So acid and water doesn't dissociate but donates water like that. This also explains, and here's a hydronium ion, this also explains why ammonia is basic. If you put ammonia with water, or rather with HCl or with water, so let's look at the water one first, it doesn't donate a proton, it's the base. It takes a proton from H+, or from H+, from water, and turns it into OH-, right? So this becomes NH4+, having taken the proton, right? So we transfer a proton from here to here, and now we have OH-. In the case of adding an acid and a base, this is very simple. The HCl donates the proton to the ammonia, so we get chloride and NH4+. So all acids and bases included in the Arrhenius definition are also Bronsted-Lowry, but the reverse is not really true.